Good morning. My name is Steve Newman. I work at Colorado State University. I'm the Greenhouse Crops Extension Specialist. Today we're going to talk about reducing energy consumption in your greenhouse, some tools that we've been working with. And Matthew Schreiner is my Master of Science graduate student, and he's going to be presenting a lot of this as is much of his graduate research project. What we're going to discuss is how to reduce your electric power consumption using a technology called variable frequency drive and how you can connect them to your exhaust fans. With exhaust fans, we're actually referring to active cooling in the greenhouse, not passive cooling in the greenhouse. Passive cooling in the greenhouse simply means opening up a vent and letting the thermal heat gradients move heat out of your greenhouse, and oftentimes, certain times of the year, that's quite adequate. But in Colorado, with our bright sunny days, and especially during our summer months, active cooling, which involves a fan, pads, and water pumps, is more common. So why do we need cooling? Well, the sun is our heat input for the earth, and we get as much as 277 BTUs per square foot per hour onto the surface of the earth on a sunny day. Coastal areas, industrial areas where there's a lot of cloud cover or haze, it's reduced to about 200 BTUs per square foot per hour. And 85% of this is going to enter in your greenhouse, and it gets trapped. And it's trapped and re-radiated as infrared heat, and this is what increases your greenhouse temperature, and it's a requirement for the cooling systems to remove that air out of your greenhouse. And here's just a schematic of the energy balance of a greenhouse. We have the sun coming in. We have both direct sun, reflected sun off the clouds, and then the electromagnetic radiation that is transmitted through the glazing of your greenhouse is absorbed by the plants, absorbed by the benches, the floors, and all the air and everything else, and re-radiated as infrared heat. And it's a challenge to get that heat out of the greenhouse. Now, active cooling systems are based on evaporative pad cooling systems, and we briefly discuss here the concept of evaporative cooling. And evaporative cooling refers to the dry bulb temperature, which is the air temperature of a standard thermometer, versus the wet bulb temperature. And the wet bulb temperature is, imagine you put a little cotton sock on the bottom of a thermometer, and the water that evaporates off that cotton sock will cool the thermometer, and that's called the wet bulb temperature. And it's a function of humidity. So the wet bulb temperature is what the air could be cooled to if the evaporative pad cooling system was working at exactly 100%. Well, we know that doesn't happen. Pad and pan cooling systems that are not designed correctly with the appropriate fan speeds, the appropriate surface areas, cool to about 80%. That's 80% of the difference between the wet bulb temperature and the dry bulb temperature. So, for instance, if your wet bulb temperature is 60 degrees and your dry bulb temperature is 70 degrees, you can cool your greenhouse to 72 degrees. What it is, it's an adiabatic process where we're converting sensible heat into latent heat. That's what reduces the temperature of the air. And for every pound of water that is evaporated in the air, we consume 1,060 BTUs of heat. This is called a Moller chart, and the Moller chart is a reference chart that we can use to understand what the wet bulb temperature does. The bottom part of the Moller chart is the dry bulb temperature. The curved part is the wet bulb temperature, and this is how we calculate the relative humidity, and straight across is the specific humidity of your water. So you can use a sling psychrometer or some simple device like that to determine what your relative humidity is. Lots of the Lots of the environmental control manufacturers work really hard to design reliable relative humidity sensors, and the better they are, of course, the more expensive they are. But I didn't want to get into a large discussion on the physics of evaporation. What we really want to talk about is how to cool your greenhouse. Now, the recommended standards by the National Greenhouse Manufacturing Association is that we want to have one air exchange in our greenhouse per minute for cooling. That means every minute we're going to remove and replace the entire volume of the greenhouse. And we calculate the volume of the greenhouse, and we account for light intensity, elevation, because at higher elevations air doesn't have the same propensity to cool the inside, and also, of course, the temperature rise that you want from one part of the greenhouse to the other. So once you calculate your total cubic feet per minute that you need to use, you can design and pick out the correct fan. The fan should be equal to the cubic feet per minute required. We usually put them on opposite sides of the pad walls so we can draw the air across the greenhouse. For efficiency purposes, we never want to have the fan to pad distance greater than 200 feet, and actually we don't want them to be much closer than 50 feet in an ideal situation. And the fans should be spaced about 25 feet apart. So here's an example of moving air across a gutter connect greenhouse, and 75 to 82 degrees, that's your 7-degree temperature rise from your cooling pad to your exhaust fan. So what part of the energy balance in your greenhouse is your fans, your ventilation? The major part of our energy footprint in a greenhouse, of course, is heat. And that's represented by either natural gas, propane, or whatever fuel you're using. Ventilation is 10% of your energy expense. I know it's a relatively small part, and as a consequence, it's not had a lot of attention over the years, but that's one of the places that we see that greenhouse growers can really cut their expenses. And I'd like to introduce Matt now to talk a little bit about some of his work.
All right, so I'm going to talk about how we can actually save some energy with cooling. Steve talked quite a bit about how much it costs and some of the inputs that raise the heat in a greenhouse and how we get that heat out. And now I want to talk about how we can actually save energy and remove that heat at a more efficiently. And so before I jump into the actual technology that my research is based on, I want to brush up on a few basics here just so we can kind of understand what's going on, throw out a few terms here. And so AC electricity, alternating current, it's what comes out of your wall sockets. It's what we plug in pretty much everywhere, is AC, or alternating current. And you can think of electrons flowing through a wire as analogous to water molecules flowing through a pipe. And whereas the AC would be the water molecules or the electrons flowing one way, then reversing directions and flowing the other way, and then continually going back and forth. And that movement is what we actually harness and use as power. Now DC, direct current, is the other type of electricity that's common. That's what we find in our portable electronics. It's what batteries use, is the direct current. And it is the, instead of the electrons going back and forth, switching directions is actually one way. The electrons just go one way. So with alternating current, we actually get a frequency of these electrons moving back and forth. And the frequency that comes out of the wall sockets is at 60 hertz. And we really don't have any control over that. And DC, direct current, as it's going one way, does not have a frequency, but we can make it look like it has a frequency, and I'll talk a little bit about that. So the exhaust fans that are used in greenhouses, almost always, I would say 99% of the industry, uses a motor that's called an AC induction motor, a three-phase induction motor. And basically, it spins due to the the change in the magnetic pole that goes around the stator, and then the rotor kind of follows that magnetic pole. And the magnetic force has actually changed positions based upon where the alternating current frequency is at. And so the rate at which the shaft spins on the motor is actually a function of the frequency that's sent to the motor. So the higher the frequency, the faster the shaft spins. Now, this is actually a convenient aspect that VFDs can take advantage of, and VFD stands for variable frequency drive. So you can kind of think about what's going to be happening with these guys. Oh yeah, so here I talked a little bit about this last slide. This is just really how a motor works, and the change in the flow of change in the direction of flow of electrons is what actually causes the magnetic force to move around the stator, which is the solid part of the motor, and then the rotor is actually what chases that magnetic field around. So what does a VFD do? Well, variable frequency drive. We actually can use it to precisely control the frequency that's sent to the motor, the exhaust motor, or whatever motor it's connected to. And the motor, these VFDs can actually be connected to a greenhouse controller. We'll talk a little bit more about the types of controllers that are usable. But they can be connected to a greenhouse controller, and they can vary the fan RPM based upon the cooling requirement. So how far away are we from our set points? We can actually increase or decrease the fan speed. And this is there's a lot of benefits to this. There's many benefits to this. One of them is the evaporative mechanism that Dr. Newman talked about. Will create a very cold and moist air rush when the typical on and off fans kick on. So what happens with the on and off fans is they kick on at full power and they're really moving some air, and then they shut off. Well, when we use our evaporative mechanism and then we turn our fans on at full blast, we get this rush of cool, moist air, and then we shut off our fans and then it just becomes stagnant. So that can actually create a little bit of a stressful environment for plants. So we can reduce the cold air, moist air rush, and we can reduce heat stress. Now I just put heat stress up there because it's actually multi-dimensions of heat stress that we can reduce. We can actually reduce heat stress in our plants because we can maintain a much more even and consistent environment, and I'll show you some data with that here in a minute. But we can also reduce heat stress in our motor, in our equipment, and we'll talk a little bit more about that due to something called inrush current. But with these VFDs, we actually really reduce the heat stress in all of our equipment, so we can actually lengthen the life of our equipment. Now, I don't really have time to do a study that long, but I would suspect if we did a study for 10 years based with different equipment, we would actually see some difference in wear and tear. Now, with these, we can actually increase crop uniformity, and that's going to be due to the fact that we can run our fan speed for longer periods of time, but at a lower RPM. So what it's actually going to do is increase mixing in the greenhouse, so we don't have dead spots, we don't have hot spots or cool spots, and so a more uniform environment is going to increase your crop uniformity. And I really think these things have a major application in a research greenhouse, due to the fact that in a research greenhouse, when we're trying to make a comparison, we really want to make sure that whole greenhouse has a very similar environment. So how does the VFD do what it does? First of all, as I mentioned, the AC signal that comes out of the wall that we plug our motors into is at 60 hertz, and we really don't have much control over that. So we have to gain control over that, and how we do that is we have to actually convert the AC to a DC signal. And what we do is the VFDs have a diode bridge and a capacitor bus, and essentially the diodes act as a one-way valve, you could think of, for the electricity. And instead of allowing electricity to flow backwards, it only allows the electricity to flow one way. And then once we put it through the bridge, we kind of end up with a messy DC signal, and we just use the capacitor bus to smooth that signal out. Now, once the electricity is in the DC type, the VFD can actually now control the frequency sent to the motor. So I mentioned earlier that DC current does not have a frequency. So how are we controlling the frequency with DC current? Well, it's a process called pulse width modulation. And what it actually does is it sends DC pulses to the motor. Each DC pulse is varying from the previous pulse, and you get DC pulses in the negative spectrum and DC pulses in the positive spectrum. As you can see, the animation is demonstrating that. The blue bars will be the DC pulses, and then the red sinusoidal wave there is what the motor will actually act like it's, or feel like it's seeing. So we actually can create a synthesized AC signal using this DC pulse, and it's something called pulse width modulation. And it's really the same concept as converting digital to analog. So precise control of fan speed. And why is this important? What can it do? During summer months, and really during winter months, during all kinds of months throughout the year, the cooling requirement can change dramatically throughout the day. From hour to hour, week to week, month to month. So why is it that pretty much all greenhouses have fans with one speed? And that's the speed with full power, taking a lot of energy. Well, these fans that have only one speed, what they do is they will, when a high set point is reached, they will kick on at full power, rush air through that greenhouse as quickly as possible until the low set point is reached, and then they will shut off. And they will do this on and off, on and off, on and off, on and off all day long. And it can be quite a bit. And that's something that we actually call short cycling. And something that I've seen is we've actually seen fans turn on and off in under a minute's time. So the short cycling is something that happens quite frequently in an on and off style greenhouse. Now, inrush current is, we've got the slide on that here, don't we? Yeah, so I'll talk a little bit more about inrush current, what it actually is. But every time a fan is turned on at full power, we get something called inrush current. And that's just the energy it takes to get that fan turning from a stop all the way up to full speed. It actually takes quite a bit more energy than the normal full amp load. And so every time we're short cycling, we're also getting inrush current. Now, these VFDs have another technology built in for energy saving, and it's something called soft starting. And what it will do is actually ramp the fan speed up over a period of about 5 seconds to full power, so that we don't get this huge rush where we just click it on at full power and wait for it to get up. We can actually slowly increase it to a period over about 5 seconds, and that will actually reduce our inrush current quite a bit. And then the last aspect of the precise control of fan speed is the affinity law, and that's a great way of saving energy, and I'll talk more about that. Oops, wrong way. There we go. So inrush current. Really, you can think of inrush current as a killer of electronics. And the reason is because during startup, and really all electronics are susceptible to this. This isn't just a motor thing, but motors, due to the friction and the inertia that they have to overcome, are very susceptible to inrush current. And it can actually create a lot of very unnecessary heat. And that's due to the fact that it is actually pulling about 10 times its normal full amp load for around 500 milliseconds. Now, that doesn't seem like a very long amount of time, but when the normal full amp load is only 2 amps, and we're pulling 20 amps for 500 milliseconds, that actually can create a lot of heat and stress on all the equipment. It also takes more energy. Oops, I keep going the wrong way. So inrush current is going to happen every time the fan is turned on. So when we have short cycling, when we have a fan turn on and off every minute or every 5 minutes, we're experiencing inrush. And we want to limit short cycling as much as we can so that we can limit the inrush current. Now with the VFDs, since we can ramp up the fan speed and down as the cooling requirement changes, we actually have the fans run longer at a lower RPM, but they run longer, so there's not this on and off. So inrush current, just because of that aspect, is highly reduced. Now, with the soft starting technology that I mentioned, inrush current is basically completely cut out. There is zero inrush current. So the VFDs really could lengthen the life of motors, all the electrical equipment in throughout the greenhouse, and they really should lengthen a lot of the equipment that's connected to them.
What's the average lifespan?
I'm sorry?
What's the average lifespan of this equipment and whatever? What's your hypothesis about?
So a lot of motors are very big that we use for these fans are big, and they actually have to be over-engineered to compensate for this inrush current. And I would say 15 years, something like that. One of the things, the VFD is not actually going to really lengthen the life of that motor because it's so much over-engineered. But if we were to use a smaller motor and save money on just having a smaller motor, we could lengthen that life of equipment by probably quite a bit. Now, I don't have time in my research to come up with anything like that. These are just pure estimates, you know, and guesses at that point. But that's why I say it could lengthen the life of the equipment. So microclimate uniformity, there can be highly variable temperatures throughout a greenhouse just due to eddies and the way mixing occurs throughout the greenhouse, just different objects, plants, structure, all that kind of stuff. And so by slowly ramping up the fan speed as needed, the fans will run for a longer period of time and actually increase the mixing in the greenhouse and reduce the difference between temperatures around the greenhouse. We're actually going to increase microclimate homogeneity. And we're also going to limit the cool air rush. It's caused by the evaporative mechanism, and that is going to greatly increase the microclimate uniformity. We're not going to have this rush and then this stagnant air. We're going to keep the mixing going. And yeah, so the evaporative cooling pad. Also, one of the things too is because these VFDs are going to be running for a little bit longer, we actually are going to allow our evaporative pad to dry down, and that is going to actually increase the life of the pad. So we're not going to have it being soaking wet with no air running through it for long periods of time. So energy efficiency, and this is really the focus of my project here. And so I keep saying that we're going to be running the fans for longer but a lower RPM. And that might not make sense as how we're going to save energy until we think about this affinity law. And the affinity law states that the change in power is proportional to the cube of the change in speed, meaning that it is on an exponential growth curve. So at 100% power, we have 100% speed. But if we kick that down to about 50% speed, we actually only need to use about 12.5% of the power. And so just kicking our fan down by half speed, we're still getting good flow rates, but just by kicking down about half speed, we're actually saving about 75% of the energy used. Now this...
Sorry, what is that picture of?
I'm going to explain that right here. So yeah, this is a data logger that we purchased, and it is measures 3-phase, and it's a continuous energy monitor, so it takes data continuously. And what it actually does is convert to kilowatt hours. So that's something that we're all familiar with. And then it does have a cost estimate there. Now it's just an estimate. You know, things change based on location and all that kind of stuff. So it is just an estimate. But it is some pretty cool data. And this is actually going to be some hard data that we can look at and say, you know, the VFD greenhouse is using this much less energy than the non-VFD greenhouse. This data logger is actually really a pretty cool piece of equipment. One other thing about this data logger is that you can actually access it on the web. There is web accessibility. And it's very highly adaptable. You can monitor up to 10 locations. We have this one just monitoring 2 locations, the VFD and then the non-VFD. It also does current usage as well as week, month, and then total accumulated usage. So this is some previous research done in 2004, and this research here is about the only research, in fact it really is the only research that I can find where VFDs have been studied in a greenhouse environment. Now, VFDs are a highly engineered product, and if you look at electrical engineering journals, you can find a lot of information and research about them, but very few, in fact, almost nobody has done this VFD research in a greenhouse setting. But this guy did some research in 2004, and the VFDs certainly have gotten better since then. But what he showed is that the electricity can be reduced by up to 36%, and also the reduced electricity consumption is based upon the ambient air temperature. And that's really logical to think about, but I just kind of want to point this stuff out here. So the crosses here are the energy usage in the VFD greenhouse, and the open boxes are the energy usage in the non-VFD greenhouse. And we see when we have low ambient temperatures, the fans aren't really running very much at all. We don't really have a very high cooling requirement. So we can see that our energy usage is almost identical in that aspect. Once we start increasing the ambient air temperature, and we have the fans, the cooling requirement is increased, we actually see this big gap between the non-VFD and the VFD greenhouse. And that's quite a bit of energy savings. We see kilowatts is on there, and that looks close to almost 10 kilowatt difference savings right there. And then once we get to higher temperatures, we do still see some savings, but the gap closes a little bit, and that's mainly because when the ambient air temperature is very high, we're actually just running our fans almost constantly at 100% RPM. So really, our big energy savings comes in this zone when the cooling requirement isn't at 100%, but it's also not at 0% when we would have short cycling from the on and off fans. Yes?
In the benefit to these temperature control fans in the winter, we do have heating that will circulate the heating properties of them, and there are similar effects.
So are you asking about using these for circulating the heat throughout the greenhouse?
Yeah.
Now these are exhaust fans. So you wouldn't really want to run an exhaust fan when you have your heater on. These are only exhaust fans, but the VFDs are very, very adaptable. They can be applied to any motor. In fact, water pumps, I think, is another very good application for them. And possibly heating, something where you had like a convective heating from like a hot water. You might want to slow that fan down for just a little bit of heat output, something like that. Certainly that's an application. And this is part of the same study as well. And this is more about the climate here. And this first one, they just measured temperature change at one point in both the VFD and the non-VFD greenhouse. The non-VFD is these darkened squares. The VFD is these open circles here. And what we can see is that the VFD maintained a much more even temperature throughout the day. There was really, only maybe 0.2 degrees worth of change at the biggest change using the VFDs. So we're actually maintaining our set point better, and we're reducing the change throughout the day. Whereas the non-VFDs, each one of these spikes, you can pretty much see what's going on here is it gets warm and then the fans kick on, and then it gets warm and then the fan kicks on, and then it gets warm and the fan kicks on. So this is a lot of short cycling right here. But you can also see that we're also changing temperature, almost 1.5 degrees Celsius within like 20 minutes, and that can be fairly stressful to plants at times. Another major aspect of this is humidity of any greenhouse environment is humidity, and again, we're just looking at the change in humidity, and also again the darkened in squares are the non-VFD, the circles are the VFD. And we again see that the humidity change is much more even and reduced in the VFD greenhouse, where in the non-VFD greenhouse we can have almost 4 kilograms or 4 grams per kilogram of water difference in the VFD greenhouse. So some of my research that I'm doing to kind of tease out the effects of the VFDs, I'm aiming to really tease out as many effects as I possibly can: climate, energy, and water use. I have 2 separate greenhouses that are identical in covering, shade cloth, the controller, the size, benches are exactly identical, the fans, motors, all that stuff. Except for one greenhouse has the VFD setup, and the other greenhouse is just the typical on and off fan. And we're using Wadsworth Envirostep controllers for both of these. And I'm going to be looking at temperature, which these guys right here are my temperature sensors. I'm going to be looking at crop uniformity and crop growth. Water use. Now, this isn't water use efficiency, just water use. I'll talk a little bit more about that. And then I have an amp clamp that actually it takes instantaneous amperage reading. I believe it's every 30 seconds, and that's really for us to look at when the fans are on and when the fans are off. So this is the Envirostep that we're using, very common greenhouse controller throughout the industry. And the main point here with these VFDs is they need this modulated voltage output. And what the modulated voltage output does is, or how it's used, is the controller changes the voltage that's sent to the VFD so the VFD knows how fast to turn the fan. That's just how the controller controls the speed of the fan. More or less communicates with the VFDs. Now, the modulated voltage output is something that's very common on greenhouse controllers. It's not just on this Envirostep. In fact, the old Step 50s have it. And I was looking at some home greenhouse controllers, you know, just some cheap, like $200-300 ones, and they also have modulated voltage output. So it's actually a very common thing to see in greenhouse controllers. One of the areas I think for future research for this VFD study is how to actually set these VFDs up. Because really, in a big greenhouse setting, when we have numerous fans on one wall, it's not really going to be feasible to set up a VFD on every single fan. What is going to be beneficial, though, is to use one VFD fan or a few VFD fans and load those VFD fans with the on and off fans and sort of use them as a buffer so that we can kick the VFD on at a low RPM, ramp it up as needed, and then once it gets to 100% power, we will actually kick on our on and off fans and run them at full power and use the VFD to sort of buffer that so we limit our short cycling. And then there's many possibilities for this VFD setup, and I think that would be something that we could really look at. So temperature, VFDs are definitely going to create a more homogeneous environment, and that's just for the fact that they're going to be running for longer periods of time. You're not going to have stagnant air. You're not going to have dead spots like you would in an on and off fan system. And maintaining set points in any greenhouse can be a challenge, especially in the summer. You know, even in the wintertime, it can be 30 degrees outside. And if we have a bright and sunny day, we'll still have to actually kick on our exhaust fans to maintain a set point so we don't get too hot. But yeah, in the summertime, maintaining the set points can be a challenge. And with these VFDs, and the uniform airflow that is increased and slowed down as needed will really help maintain the set point. And that's evidenced in the previous research that I showed. So I have some temperature sensors I showed that picture of. I actually have 10 sensors, and I'm going to be doing a couple different things. One of them I'm going to be actually comparing the difference in change between the non-VFD and the VFD greenhouse. And then I'm also going to use all 10 in both greenhouses to monitor difference in locational temperatures around the greenhouse. And this is kind of my temp sensor placement, where they're going to be looking at. The bench system has changed since this diagram was made. Now we have roll top benches, so there's a few of them, so that's why they kind of look like they're hanging off there. But that's just where they'll be monitored. And now I can't monitor the whole greenhouse just because of limited sensors, but I feel like monitoring at least half of the greenhouse will get us a good idea of what's going on. So I mentioned something about water use, and I really believe that these VFDs are going to reduce the water used and evaporated off the soil surface and evapotranspirated through the plants. And the plants, I think there's a couple of physiological things going on there. But the soil surface is mainly because it's going to be maintained a more even temperature and humidity. We're not going to have so much evaporation. There's just going to be less plant stress, so that is also going to reduce the water use. And so I have a hanging lysimeter set up, and basically it just is these cells that I have connected to these pots, and it just takes a weight, basically a weight every 5 minutes. And so we can actually monitor how much water is being lost. And what we'll do is we will compare the slope of the line from the VFD and the non. I actually have two data loggers, so we're doing simultaneous comparisons. So the slope of the line of the water loss should actually be quite a bit lower in the VFD greenhouse. Oh, here's a picture of it right here. little bit closer. So you can see the plant's actually hanging. We have the top here. This is just a force displacement cell. These are all connected to a Campbell CR1000 data logger. And I have 6 plants in each greenhouse for simultaneous monitoring. So energy measurements. This is the amp clamp data with the Hobo U12. This is a very common data logger, very easy setup. And this amp clamp just takes an instantaneous amp data. It's not continuous like the other data logger I showed you. And it's every 30 seconds, and we're really just using this to see when the fans are on, when the fans are off, and the VFDs, how fast or how high they're actually running. We do have these set up in both the VFD and the non-VFD greenhouse. So this is some data that I have extracted from the amp clamps. It's actually very interesting. There's a couple of things I want to point out here. And so the top set of data is the on-off greenhouse, typical on-off greenhouse, and the bottom data is from the VFD greenhouse. And the first thing I want to point out is if we look in the VFD, and these are all at the same time frame, we look at the VFD and we have this long period of time where the fan has been running and hasn't really shut off. We can kind of see changes up and down here where the fan is increasing speed, decreasing speed as needed. We look up top here at the same time frame and we have this continuous on-off, 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 on-off all day long. We can see that this whole top data is really just a bunch of blue bars, meaning that there's a very, very high amount of short cycling going on. We can just look at this and intuitively see that we're reducing short cycling with the VFDs, also saving energy. Another thing I want to point out is I talked about inrush current, and I feel pretty lucky to have gotten this data, but these spikes right here are actually where the amp clamp was actually took data exactly when that fan turned on. So we were actually fortunate enough to capture some of this inrush current, and we can see these big spikes all the way up here, quite a bit more than the normal full amp load. Now we don't see any down here in the VFDs, but what I want to point out is just because we don't see these these spikes on every single one of these on-off cycles, it's still there. This inrush current is happening every single time we see an on cycle from the fans, where the inrush current is basically eliminated with the VFDs. So that's my research there. Okay, so this is the little bit more about the energy usage monitor. These are very adaptable. They can monitor 3-phase, 2-phase, single phase, and they can actually connect up to 10 separate locations on this guy. So we can do simultaneous monitoring between multiple different points. And the big thing about this is that it really it converts to the kilowatt hour units, so that we can really get a good cost estimate and a good estimate of how much power we're actually reducing. It also has a current usage as well as accumulated, and it'll step it back from yesterday, last week, last month, and total accumulation. And you can actually buy an adapter for this and connect it to the web and access this data just from a website, anywhere there's internet access. So pretty cool little piece of equipment there. So the fan control requirements with this, for a VFD, is just the modulated voltage output. I talked a little bit about that. And it's really just a percentage of the voltage output is similar to the mixing or steam valve, which is like the older Wadsworth Step 50s use the modulated voltage output for a steam valve, but that can also be applied to a VFD very easily. It's actually identical, 0 to 10 volts. And it very easily integrates into controllers, many types of controllers. Not all controllers, but many types of controllers this will work with. And so that we can actually change the fan speed based on the demand. These are a couple websites here for you. This top one will be the recording of this lecture that we gave here, and then our Colorado State Greenhouse Extension website.